Hey everybody, welcome back to Young Engineers of Today. I hope you had a good couple of days, and I hope you are ready to continue along with more 3D modeling stuff. But we're taking a different tack. We're not doing more Fusion 360 today. We're getting started on something called 123D Make. And by getting started, I mean we're going to do a lesson today, and then we're going to start on something new next week. Um, just so you guys know, I believe next week should be more about Python and Raspberry Pi, and that'll be like the next few weeks. It should be pretty interesting. It should be pretty fun. So, get excited for that because woo woo programming. I guess I could have sounded more excited about it. I like programming, otherwise I wouldn't become a computer science major. But um, that's what we're doing the next couple weeks. I think it should be pretty cool. Today is pretty much going to be about learning how to use 123D Make, sort of understanding the basic controls and things like that, getting your first print prepared. Um, I mean, if you wanted to, you could print it out at home, but that's not really, that would be tricky with how we're going to do it today. Um, you'll see what I mean later on. It'll make more sense. But we're going to, spend a little bit of time talking about laser cutters for reasons that you'll see. What 123D Make is, installing it, and get your first project done. Should be pretty cool. Anyway, laser cutters. Laser cutters were first pioneered in 1965, like the first ones were used. And they were mainly used to cut holes in diamonds because at the time, as I'm sure you guys know, diamonds cut through pretty much anything. So a lot of engravers and etchers and things like that will use diamond tips on them so that they can make a good. They're good at scratching. They can make a good you know engraving. I wasn't sure if I was trying to find another word for it, but oh well. But how do you like easily cut those diamonds like in a cost-effective manner? Well, laser cutters can do that. They can put holes in diamonds and they can, make them pointed and just all kinds of stuff. Nowadays, there are a few different types of lasers used in laser cutters. The most common is carbon dioxide, CO2, which refers to the type of gas that is pumped through the laser head. Um, you can have a few different ones. There's like an argon gas mixture, which has a few different things in it. It's actually a pretty interesting mixture. There's, I believe, a neodymium, which doesn't. It's not the gas, but the neodymium, I believe, refers to the way that the laser beam is focused, and the electrons are excited. Anyway, or photons, excuse me. Anyway, laser cutters are good because they offer more precise and versatile cuttings than other known or means to cut than other known methods, which we'll get into in a little bit. In essence, though, a laser cutter basically just creates a beam of light, and it bends or bounces that light. You bounces really. Bending in this case would just be using a mirror, like bouncing would be, until the light is really focused, and then maybe set up a focal length with a lens, and heat the metal, and then that's how you cut. And when I say focusing with it, show of hands, how many of you wear glasses or contacts or whatever? Okay, so you guys understand that, like the basic way that well, I'm sure all of you guys understand that the basic way like light enters your eyes is your eyeball creates. It basically bends the light so it all focuses at a point, and that point is the cones and the rods in your eye, which take in light and color, and then your brain translates that into images and stuff like that. And then maybe the reason that you might wear glasses is because it doesn't exactly focus to a point where those cones and rods are. Using eyeglasses, you can focus it so that you change the focal length. That is where the point focuses. It might be a little bit longer, but that accounts for the extra space required because you're wearing glasses, and then it focuses right where it's supposed to in your eye. It's the same deal here. If we're talking about a focal length of a laser, it's the point where the laser is at its most energetic and thinnest, or thinnest as far as diameter is concerned. And it's the most energetic because it's still the same laser, it's all just down at one point now. So there is an effective length to keep the laser from the material that you're cutting. If you have it too far away, it's not really going to work. If you have it too close, it's not really going to work, unless, of course, you adjust the focal length. So that's where the lenses come in with the focusing. Now the gas in this instance, the laser gas that is here, this laser gas sounds actually kind of really extreme. I don't know, like super cool. Excuse me. So the laser gas can be used to either be something that actually kind of catches fire and turns into a plasma when the laser hits it, so it increases in temperature and helps burn through stronger metals. Or it can just be used to blow through the nozzle and blow away hot metal that's there. So the cut is clean, and we ensure that, you know, like no residual hot metal is still attached, and it cools down, and then it just kind of like you basically accomplished nothing because there's still a metal connection between the two pieces that you were trying to cut. And there are a few different types of laser cutters. Now this is distinct from the types of lasers used in laser cutters. These are methods of cutting. So there's vaporization cutting, which is your most basic one. You melt stuff, and basically the melting of the stuff heats it up, causes gases to expand inside of it, causes the metal to expand, and it actually clears more space and sort of evacuates itself so that you can cut further into it. Melt and blow is when, you know, the gassing of the metal, the heating of the metal isn't quite enough to clear out the area and dig, you know, and cut out more. So you melt stuff, and then you would blow it away with air. Unfortunately, not explosions like it might sound like, which disappoints Mr. Torg, but oh well. Then there's thermal stress cracking, in which you heat stuff up, but instead of it melting, it cracks, like glass. You heat it up to a certain temperature, it's going to crack instead of... and you heat it up quickly enough, it's going to crack instead of melting. And so, like when you use a laser cutter to cut glass, that's actually what's happening is you're creating little tiny cracks, and you're just doing it quickly enough, and you're moving along so that they're guided cracks. And it looks, to, you know, our eyes at least, like a nice clean cut, when in reality it's just tons and tons of tiny little cracks. And then you've got something called stealth dicing, which is used for computer chips. This is, you know, if you really want to create super small microchips, and the traditional die cutting methods aren't quite enough, you can use laser cutters in order to make even smaller integrated chips. Why it's called stealth dicing, I don't really know. It might be because you're creating chips that are so small it's hard to tell where you're cutting, or it happens so quickly you're not really sure that it's happening. I don't know. Maybe. No idea. And then reactive cutting. Reactive cutting is kind of like that heating up the gas and creating a plasma. It's not a plasma. It's different from plasma torch cutting, which is what's generally used to cut thicker metals. Reaction cutting or reactive cutting is relatively new as far as laser cutters are concerned. It's been a long time now that laser cutters have not been able to cut through metal that's thicker than about 1 millimeter, but and that's generally been in the purview of laser cut or laser torch cutting, where you take a gas and you heat it up so much it becomes plasma, or plasma torch, not laser torch. Plasma torch cutting, where you heat up a gas so much it becomes plasma, and it cuts through the metal. And yes, this is, I mean, in theory at least, it's the plasma of sci-fi and stuff like that. Now, a lot of times when science fiction uses plasma, it depends on the author, but I think they don't really know what plasma is. So plasma can do all kinds of stuff that doesn't really make any sense, but plasma is a real thing. It's actually, according to many people, it's another state of matter. It's superheated gas that behaves differently than actual gas does, or air. So we've got lasers and plasma in modern society. I mean, come on. We've got we've got Star Wars pretty much down. Now we just need to put the plasma inside a sword and you've got a lightsaber. No big deal. No problem at all. Laser cutters come with a few advantages. One being that they're cheap. Relative to many other methods used to cut metals, they're cheap. Relative to many methods of cutting metals, they're easy to use. Um, they can make cuts just 1/10 of a millimeter thick. So, like, what that's called is the kerf, and that is the separation between the two objects created by the cut, literally the size of the cut. Think of using like an X-Acto knife and cutting through cardboard or something like that. You know how the cardboard will part because the X-Acto knife is cutting through it, especially if you press down pretty far. Um, that, in a sense, is kind of like kerf, uh, and it's KERF, but it's literally just the size of the cut. And laser cutters can create, or laser cutters, yeah, have a kerf that is 1/10 of a millimeter. So if you have a ruler handy that has like a metric thing on it, that's 1/10 of the tiniest markings on the metric side, which is pretty impressive. And it's also useful in many materials. So, it's useful for glass, it's useful for metal, it's useful for cardboard. You can use it on wood, you can use it on all kinds of stuff. Laser cutters will work with all of those things, and that's another advantage of it, because otherwise you got to have like tons of cutting equipment. Like you might want a lathe and an arc welder and a plasma cutter and scissors and saws and glass cutters and things like that. And you just throw all that stuff out, get a laser cutter. No big deal. So far we've looked at 3D modeling, which is good for 3D printing and CNC machines. Among other things. Like, it's also good for prototyping. It's also good for designing things, creating models that you can use in games and stuff like that. It's good for a lot of things. But what if we only had cardboard and a laser cutter, an aforementioned laser cutter, or a pair of scissors, or some paper, or whatever? What if we didn't have a 3D printer or a CNC machine to work with? Well, enter 123D Make. Make uses 3D models, so you can import your models from Fusion 360 or AutoCAD or Tinkercad or SolidWorks or SketchUp or whatever. You can import those models and then use them in Make. You can use models from Blender, all kinds of things. But basically what it does is it slices up the model into a bunch of different layers. Like this example here, this rhino head was probably a nice, like, smooth 3D model. I don't know how well you can see it. Like, I don't know what the resolution is coming through. But as you can see, it's separated into a bunch of different horizontal layers, all stacked on top of one another. So it slices the model up into a bunch of different layers, and then it places all the layers on a flat plane. In this case, on like a piece of paper or a piece of cardboard or something like that. All of these layers are then printed out or cut out onto material, and then you cut out the pieces and you put it together. So then this is the final cardboard model of the rhino head, which was set up here in Make. So you could build a physical model of a 3D thing using just cardboard and something to cut it with, and maybe glue. Glue would probably be a good idea. Not necessary, but probably a good idea. But yeah, you would cut the pieces out and put it together like a puzzle. And it's free, which is pretty awesome. So I'm going to go ahead and copy the link URL and put it into the chat box so you guys can pull up the website. And when you do, you should see something that looks like this webpage here, somewhat. Go ahead and pick your operating system on the right hand side with the 3 buttons. I know it's only PC or Mac. If you're running Linux, you should be able to run it on Wine, I imagine. If you're not running Linux, well, then that shouldn't be a problem. You can either do PC or Mac. And it should take a few minutes to to download, so go ahead and start downloading it, and when it's done downloading it, open it and install it. I'm just going to spend some time talking about some stuff in the meantime. Not the least of which is the model that we're going to use today. So let's actually handle that real quick too. We're going to get ourselves an STL file that we can use in Make. So I pasted an Instructables link here. And then this should actually give, like, the first picture actually is a good representation of what Make is meant to do. This is the final product built out of cardboard. But if you scroll down a little bit, there's the first step, Startup 123D Make. Scroll down to the bottom of step 1. Not all the way to the bottom of the page, but just the bottom of step 1. And you should see a file here that's 2304 Tyrannosaurus Rex ASCII.stl. And it's 6 megs. So click on that, and you should download that as well. But we're going to want to download that too. So right now we should be downloading 123D Make and an STL file. So what exactly is an STL file? I mean, why the weird name? What does it mean? What does it have in it? Well, STL stands for stereolithography because, you know, gotta have that T in there. Anyway, yeah, it stands for stereolithography. And basically it contains written instructions for drawing a bunch of triangles in a certain order. Like, okay, if we were to open up this STL file in a new tab, you'll notice it's just a bunch of text now. And you'll notice that we've got like these vertexes, and they're all in groups of 3, and each of these vertexes have 3 sets of numbers, and then you got a facet that's 3 sets of numbers, and it just keeps going and going and going and going and going and going and going. Oh my god, there's so much stuff. Well, what those are those written in, let me try that again. What those are written instructions for drawing a bunch of triangles in a certain order. So like, what they are is like, oh, okay, so this, you know, let's say we pull in the first coordinate and it's meant to go like right there, like right there, and then the second coordinate is meant to go right there, and the third coordinate is meant to go right there, and those are the coordinates for your first triangle. Now the important thing about STL files is the triangles that they give you are one right after the other, and they're all next to the previous one. So you'll get another set of 3 coordinates, and they'll have some overlap. So you can draw a second triangle with it, and you'll get another set of 3 coordinates, and you can draw a third triangle with it. You know, and it has that in common with the previous triangle, and you'll get another set of, you get the idea. And you start just drawing all kinds of triangles, and the end result is these triangles make up the model you made in the 3D modeling software or whatever. The whole idea being, you know, in 3D graphics and stuff like that on computers, all they are is just a bunch of different triangles being projected. They're all actually the same size, so this is not correct, but it's close enough to give you an idea of what I mean. But anyway, a 3D model is made up of flat triangles, all just kind of placed next to one another. Now, you might be saying, okay, so say I have like some kind of curved surface or something like that. How do you represent that with flat triangles? Well, I'm glad you asked, because the answer is you use a lot of them, and you use really small ones. So then you just have a bunch of tiny triangles. Because even though they're all triangles and they're all flat, if you have enough of them and they're small enough, eventually your eye basically can't tell the difference, and it all looks like a nicely curved plane to you. So that's why if you've ever looked at 3D models or if you've ever seen somebody talking about character models in a video game or anything like that, they start talking about stuff like tries. Tries are short for triangles, and it basically means however many triangles represent the model. The model could be, 30,000 tries or something like that, and it's just this super complex, like, detailed model. Or it could be 3,000 tries, and it looks weird and blocky and pointy like a Nintendo 64 game, or a PlayStation 1 game, that kind of a thing. Basically, the more triangles you have, the more detail you can have in your model. Now, that's not to say that the texture doesn't have anything to do with it either, because the texture will also need to be detailed, otherwise things will look weird. But that's basically what drives 3D graphics nowadays, and what determines how detailed a model is how many triangles it uses to make up the model. So, show of hands, who's already got it downloaded and installed? Okay, one hand. How about just downloaded and it's installing right now? Two hands. Alright, cool. Well, I'm going to go ahead and open up 123D Make. Once it's done installing, you guys do that too. It's going to take me a minute anyway, and I'm going to go through this stuff pretty slowly, just so we know that, like, you guys can get caught up in the meantime. So, I guess that screenshot should maybe look familiar. I made this one. I made this. Okay, so yeah, it's going to spend some time processing. Thankfully, it starts up much faster than Fusion does. Fusion took forever for my computer. Anyway, you guys will not be seeing a blank screen like mine. You will be seeing this sitting in the middle of the screen. So you remember that whole thing about agreeing to licenses? And like the license and services agreements, and how it's like, oh, it would take somebody 3 months straight in order to read through all of... Yep. Go ahead and just click agree. we're not gonna have you read it now. Then you should see like a splash screen come up. Not really a splash screen, but like an info screen. And it should have this little sort of infographic here, which looks a lot like something I might have used previous in the slideshow. Hey, what do you know? It's that. It's basically just explaining in 3 very basic steps what Make is supposed to do, and what you are meant to do with Make. There's a few other things on there, but we're going to basically go through all of the information that it conveys in that window anyway, and in more detail. So just go ahead and click the red X at the bottom to close it out. Or at the top, doesn't really matter. But anyway, once all that's done, you should be looking at a blank screen now. Like just one button and a couple other things. So let's take a look at what some of this stuff represents. So first of all, you've got this cleverly hidden menu up here. If you mouse over the Make icon, it turns into a menu where you can, do your basic file menu options, including saving it, exporting a mesh, and 3D printing it, which I feel like defeats the purpose of Make, but, whatever. And then you've got, next to it, you've got these 2 arrows. These are your undo and redo buttons. And it should be noted, this is an important point, the undo and redo key commands, keyboard shortcuts, don't work in Make. So you have to use these buttons up here. You can't Control Z and either Control Y or Control Shift Z, depending on what program it is. But you can't do those. You have to use the undo and redo buttons. They just don't work. Nothing happens, but at the same time, nothing happens. So you'd just be sitting there mashing Control Z and nothing's happening. Anyway, over here you can sign into your Autodesk cloud accounts. So you would use the Autodesk ID that you set up for Fusion 360, and you could sign in there. You don't have to do that now, but you That's a thing you could do, and if you want to save it to your computer or export it even, it will require you to sign in later, so we'll just cross that bridge when we get there. And then over here you have a help menu, which, just gives you various things. Alright, so, you guys got that software installed yet? Okay, got one hand up. How about you, Kai? Still working on installing it? Alright, excellent. Perfect. Everybody's got it installed. That's what I like to see. Alright, so let's make this screen a little bit more interesting. We're going to click on Import under Model. And it's going to bring up a, blah, blah, blah. You can open up all your stuff. We're going to go down to the STL file that we downloaded. Mine's on my desktop because I saved it there. Your guys' might be in the Downloads folder. It's basically wherever you saved it to. So go ahead and locate it. It's 2304 Tyrannosaurus Rex ASCII.stl. Click on it and hit Open. And it'll spend, a few seconds just processing and thinking and importing and working and, get the idea. And then you will get a Tyrannosaurus Rex doing a trick on its tail. But, now's a good moment to take a look at some of the controls that you can do. So with the mouse key, with the mouse keys, good lord, the mouse buttons, if you hold down right click and move your mouse, you can rotate it. You can use the mouse wheel to zoom in and out, and you can hold down the mouse wheel or a middle mouse button in order to pan around. So click and hold to pan, roll to zoom, click and hold right click to rotate, or as they call it, tumble. So many people call it rotate. I don't know why they decided that tumble was a better idea, but sure, whatever. Now, if, let's say you're working on a laptop or something like that, and you don't necessarily have those keys, that's okay. On the right-hand side of the screen, now that the model's been loaded, you should notice a few new things. First of all, this cube should look pretty familiar. From our experiences with Fusion, this should be a no-brainer. So, you can click on the various things like you can with Fusion and rotate it to those specific angles, or you can just click and drag and move it around. You can also click on this first icon here in order to rotate it. Just click once, and then it should bring up the icon, and then drag with left mouse button. Pan is right beneath it. It's the hand. Same idea. Click and drag with the left mouse button. Zoom is right below the hand as the magnifying glass. Same idea. Click and hold with the left mouse button. I think you're sensing a pattern here. Now let's say we pan all the way off. We could click on this one that has like a rectangle with like 4 bent lines around it, and that'll recenter the model in the middle of the screen. Basically just show a model on screen. And then the last one beneath it, this it looks kind of like those 3 planes that we had in Fusion. This one's kind of interesting. So what this does is it switches the type of projection that the model has. Like, it looks like it's not really doing much, like the dinosaur gets kind of deformed and that's it. But if you look at it from different angles, sometimes you get like a better idea. So basically what these mean is the first one is, I believe, orthographic, and then the second one is perspective. I believe. It's not really clear which one is which, although it would make more sense to me that this was perspective and the second one was orthographic, but hey, what do I know? I'm just a guy who didn't make this program. Anyway, really the reason for them is perspective is useful for looking at your model from a certain perspective and getting an idea of the, sorry about hitting my microphone, an idea of the proportions from that angle, so like things look right. And then orthographic is making sure that everything on your model, like it's easier to make sure that everything on your model is connected to everything else. Make sure that there aren't any like open disconnected parts of the model. Like maybe his arm isn't floating in the air or something like that. And if you zoom like way in on the dinosaur, you can see the triangles I was talking about. So you got all these triangles right here. There's actually triangles right here, but they're the same color, so it's hard to tell. That's exactly what I'm talking about. If we had more triangles, this dinosaur would look smoother. But for now, it's kind of a neato thing. Neato thing. Anyway, we've looked at that stuff. Let's look at this stuff on the right. So we've noticed that the dinosaur is sitting on his tail, and the way we can tell is because the shadow is being cast underneath the dinosaur like this. Unless, you know, he lives in some sort of strange world where there's no overhead light and there's just light in front of the dinosaur, which is possible. I mean, maybe there's a spotlight right there, but as it stands right now, he's sitting on his tail. That's fine. No big deal. But if you wanted to, this circular arrow in the model area, if you right-click on the STL file and select Save As, that should do it. Sorry about that. I forget sometimes that it doesn't default to doing that. Save file or save link as, one of the two. They both mean the same thing. But yeah, so he's sitting on his tail. So if we click on the circular arrow in the model area, he rotates. So now he's sitting on his feet. And he rotates 90 degrees each time, so we could have him sitting on his face or on his back or whatever. But I'm gonna have him sitting on his feet just because, I like to give him a little bit of dignity like that. He's already got tiny arms. Give him whatever he can get. Next, you got manufacturing settings. And manufacturing settings is more just about the size of the material that you're going to be printing the flat planes onto, the slices onto, or cutting them out from, as the case may be. So, you can print it out on letter-sized paper, or legal paper, or, just a whole bunch of different sizes, A4 paper. For now, what we're going to do is we're going to select, we're going to select B1. B1 is the largest size, and you'll notice it's about 1/5 of an inch thick. So it's about, it's not quite 1/5 of an inch thick, but it's close to it. It's about the thickness of cardboard. So that should work out nicely for us. In fact, all of these options are about 1/5 of an inch thick, but, B1 is going to have the dimensions that we need. Alright, and then the next bit is the object size right here. Well, this one's pretty self-explanatory. If you change one aspect of the object size, at least right now, everything else scales in order to keep the same, the same ratio of sizes. So if you make the length shorter, the width will go down, and so will the height, in order to accommodate, so that we don't have like a squat dinosaur or something like that. So you can go ahead and mess around with that, although whether or not you mess around with it, as soon as you're done looking at object size, click on the original size button, and it will bring the Tyrannosaurus back to the original size of the model, which is an important thing. For some reason, at least on mine, it didn't actually import it as the original size, so we want to make sure that it is the original size, the length of 28 inches. So uniform scale will keep everything uniform. If you uncheck it and you change the length or something like that, the other stuff will not shrink to accommodate, and original size will just bring it back to its original size. Pretty self-explanatory. Under units, obviously you can change the units that it's in if you are used to working in something else. Whatever. So that brings us to construction technique. That's the last thing on here, and it's got a few things going on with it, so we're going to take a couple of minutes to look at it before we start messing around with it. You can click on the drop-down menu to see what's in there, Like even if you right click on it and save file, it won't download? Huh, that's annoying. Um, okay, well, I'll show you the thing that I was going to show you guys at the end of the lesson, just so we're all on the same page with that. You could try Thingiverse, and that goes for everybody. You know, if you really don't like a dinosaur, you can download something from Thingiverse while we're talking about this. Just thingiverse.com. It's full of STL files. It's full of models and stuff like that that you can download and mess around with. So you can find something on there that's maybe more appealing, or at least downloadable, and import that into Make. So that's an option. And I'm sure you've already got it, but just in case. There you go. Alright, so construction technique. Yeah, you can click on the drop-down menu, see what's in there, but what does that stuff all mean? It's just a bunch of, stuff or whatever. Well, each of those options listed changes the way that Make slices up, or in some cases doesn't slice up, your model. This in turn changes how it fits on the paper, or cardboard, as it may be, and how it's constructed physically, so how you would assemble all of the pieces together. So let's take a look. You've got stacked slices, which is like the most basic one. It's basically just horizontal slices all on top of one another. You've got interlocked slices, which is horizontal and vertical slices. So, if you're working with something like a cube or something like that, you can do interlock slices, and it might reduce the amount of material that you're using, which might be, useful. You've got curve, which creates like ribs that you can sort of, they all kind of lock into each other. Like, there's always a thing I'm trying to look for here, an example in my head, but I can't think of how to explain it. The closest I can think of are like those wooden puzzles that you try and take apart, but everything's sort of like interlocked with everything else. And so it's like you pull on one thing and it might like loosen up another thing, but then there's a third thing which is keeping it from opening up, and so you gotta kind of like pull on three things at once in order to loosen everything up, and it all kind of falls apart. It's kind of like curve. That was a weird description. It's kind of like curve in the sense that everything sort of locks in, and there's little structural ribbings and things like that to give it a more of an organic shape and b a decent amount of strength. And then you got radial slices. As you can see, the slices are like these stack slices, they're going this way. These interlock slices, they're going, both of those ways, and these radial slices are going around and around. And then you got like these coming out from the middle in order to, provide some extra support and things like that. So that's radial. Radial slices is just a different type of slices. And then folded panels are actually pretty interesting. At least I think it's kind of cool. I want to mess around with it at some point. Folded panels are like, have you ever dealt with those pieces of paper, and it's like the 6 panels, and then you want to fold them up, and they make a 6-sided die? That was supposed to be 2 squares. Jeez. Alright, I'm just going to quit while I'm ahead. But anyway, like, you take the piece of paper and you fold it, so like you've got everything kind of being folded upwards. And these are all the panels here. It's just, you creased it here, and you creased it here, and here, and here, and it all kind of folds up into a cube. That's not a cube. How do I draw cubes? Okay, you know what? Let's pretend that's a cube. Look at that. Look at all of its equal sides. Man, I'm good at drawing cubes. That looks closer, but it's still like a weird rectangular boxy thing. Anyway, they all fold up and they create a cube. So, you know, this might have like one right here. This might have two. And you get the idea. That's what folded panels does, is it comes out flat, all like very like elongated and stretched out, and then you can fold those panels at the specified points, and then you get a 3D model. And then 3D slices, I assume, is just a sort of more detailed, stacked slices. So these are all the options we have as far as slicing up the model. For now, though, we're going to select stack slices because this is basic. This is meant to be an intro. So stacked slices. And oh my goodness, what have you done? You've broken the dinosaur. What if everything is wrong now? No, I'm just kidding. Of course, because there's no way I'd know. But that was supposed to happen. So these are rough slices of the dinosaur model, which is somewhat similar to what the finished product would look like. So if you were to build this out of cardboard, this would be a vague sort of idea of what the final product would look like. Now you'll notice that there are blue parts here, like on his chin and his arms and his dinosaur ears. Are those supposed to be? Oh, it's the tops of his head, like the very tops. Anyway, my model was too small, so those parts will turn blue, and that means that those parts will fall off. They're too small to attach to the model, and they'll just fall right off if you try and build it. So if you get a lot of the blue stuff, it might be that the model's too small. You might need to reset the model to original size. But even then, you should still get probably some blue stuff. Like, notice all of his teeth are blue, so all of his teeth are going to fall out. Poor guy. It's like his livelihood. And his fingers are going to fall off, so he doesn't even have that going for him. And the top of his tail isn't even really going to work. This dinosaur is going to have a really bad day. Like a really bad day when he gets built. So let's, fix some of that, because I'd really, rather not have this dinosaur like have his teeth all fall out. That's no good. So what we can do is we can go right down here to slice direction. It's the first one underneath construction technique and dowels and all that. So go to slice direction, and you should get these two circles around your dinosaur. And there's one going around him like the middle from front to back. So it's the middle there. It's this blue one. You're going to want to click on the blue one. And then you're going to want to, down here at the bottom, there's this rotate by angle thing which appears when you click on slice direction. So click on the blue ring, and then down here at rotate by angle, hit 90. And it should automatically update. Not if you don't hit enter. Hit enter after you hit 90. It should automatically update. And you'll notice something different about this. Hey. The slice direction has rotated. Now the slices are going vertically. So, you've got all kinds of... And we're still going to have some blue stuff. That's okay. That stuff's less important. He's still going to have his teeth. He's... the claws, with some glue should stay on just fine. The end of the tail, like right there, not a big deal, Again, with some glue it should be okay. If, you accidentally hit in like 91 or something like that, or you click on the wrong ring to rotate and the slices go in a funky direction, that's okay. You can just click on reset over here, and it will bring it back to the original orientation. And then you can, fix it from there. So no big deal if that happens. Reset's also good in case you take a look at it and you go, I don't really like that. You can just hit reset, start from, square one and do a different rotation from there, which sometimes is easier than having to do math to figure out how much you need to rotate it in order to test a different angle out, or whatever. So now we've got our slice direction in. Well, that's pretty cool. We already changed the size here to B1 27.83 by 39.37 by 0.17. So, under manufacturing settings, set it to B1. We already rotated the slices. And we already did the, yep, we already did that. Yes, this is true. You may have, and you probably, in fact, already noticed these off to the right. These are kind of like a print preview of what the sheets will look like if you decide that this is how you want it, you want your dinosaur to look. So as you can see, each one of these is a different slice of the dinosaur, a different horizontal slice of the dinosaur laid out on the sheet. It'll be either cut by a laser cutter or, by your deft hands, in which case you can then, assemble it into a dinosaur and mess around with that. But what do these numbers mean? Like 25 and 17 and 23 and 22. Like what does that mean? Well, I'm glad you asked. I will show you. Maybe that wasn't meant to be creepy, but it kind of came out creepy. I'm sorry. If you click on Assembly Steps, which is just two options beneath Slice Direction, Assembly Steps, you should see like a cardboard dinosaur now. That's what this is. In fact, this is digital cardboard, which is kind of hilarious. You should see a cardboard dinosaur now. If you drag the slider at the bottom, you'll notice that pieces start flying off to the side, all the way until you've got just a toe, just a dinosaur toe right there, nothing else. So go ahead and start dragging it back. And this is in fact the instructions on constructing this dinosaur created by Make. So they're all like, okay, so this is step 8 if you want to construct this dinosaur, and here's step 9 and step 10. And handily, it actually lights up which piece is the one used in this step. So if we go back to step 11, boom, there you go. You might also, in fact, you've probably also noticed that some of these pieces are hyphenated, like 11-3, 13-9, 29-5. In fact, most of them are hyphenated. What that means is these all get applied on the same step, like they're on the same layer. So as you notice, for example here, 11-1, let's go back one more so we can see it being applied. 11-1, that piece goes right there. Let's rotate it to the side a little bit. Okay, that's really hard to tell, so I'm going to zoom in. So 11-1 was this piece right here. 11-2 is that piece down there. And 11-3 is this piece right here. So they're all on that same plane. They're all the same slice. However, they're not connected to each other. They're all three separate pieces. They're just on the same layer. So it splits them up into hyphenated steps. So that basically anything that's like all of the other 18s will be on the same plane as 18-1, but they're just not connected to each other. So as you can see, there's a lot of hyphenated steps in this dinosaur because he's a pretty complex model. You'll also notice that there are some items that are just sort of being placed in empty space and left to float there. You know, don't worry about that too much. It just basically, the upshot of it is when you get to a step where things should be attached to one another, then you're going to attach them in roughly the spot they should be attached. Like so that it makes sense. Anyway, you can, drag the slider to watch your dinosaur get built layer by layer and see the finished product. And over here on the drop down menu, you can change it to plywood, you can change it to plastic, you can change it to all kinds of stuff. Though plastic is a little bit hard to tell what is going on. So anyway, let's say we are satisfied with this design. We think this is a pretty cool looking dinosaur. We want to use this stuff. He's going to be made out of plastic. This is going to work out just fine. Start of a beautiful friendship between you and, Mr. Sliceosaur right here. Well, the last thing you can click on, the last option here, Get Plans. Go ahead and click that. And it should bring up 3 sheets. Well, these 3 sheets are the 3 sheets over here. This is a preview, again, of the final product. But you notice you got some stuff down here. You got file type, EPS, inches, and then you got export and you got print. So if, you had a printer and this was paper, you could print it out on the printer. And it would, place the design down on the pieces of paper so that you cut them out and build them yourselves. Exports it as an EPS file type, which can be used on laser cutters and the like. So, you can go ahead and click on export. It'll ask you to log into your Autodesk account and then find a place to save it, give it a name that you'll remember. And the reason I bring this up is because there's another point. They save as zip files. The reason why is they save as zip files that you can unzip, and they have the EPS files inside. So the individual sheets are EPS files inside of one zip file, which is whatever the name you gave it. So if you call it Hot Diggity Dinosaur, and save it to the desktop. And there you go, Hot Diggity Dinosaur. And you open it up, and there's 0, 1, and 2, the EPS files. And, believe it or not, there you have it. That's basically the minimum you need to know to start creating your own projects. You can mess around with other stuff and make and see if there's a design you particularly like and doesn't generate a whole lot of blue stuff and all that kind of a thing. But, if you're satisfied with it, you can have it be laser cut onto cardboard and assemble your dinosaur with glue and 3D print, or 3D pins, as opposed to those two-dimensional pins that you hear about. Glue and pins, and that's it. You'd have a finished product at that point. So I think that's pretty cool. And yeah, and was the last point, Thingiverse. You could go to Thingiverse and you can mess around with the different designs and check them out and see if there's anything that catches your fancy. Thingiverse with an H. Not Tingiverse. But yeah, like Halloween stuff, small things. So like Halloween collection, you could print out like this jack-o'-lantern. Like the slices of the jack-o'-lantern. And assemble it, or like this skull here that might actually be kind of cool. Or like a tiny chair for tiny people for stuff. Or a tiny antique Scandinavian stove, because you didn't know it until now, but you needed that in your life. Or a miniature Queen Anne Chase lounge. Anyway, you get the idea. I got kind of caught up in the things that were here because I wasn't anticipating such specificity. But anyway, that does it. I'm going to go ahead and ask the poll questions. And once those are done, it will be the requisite question time for you guys if you have any, and if you don't have any, then you're free to head out and just, have a wonderful weekend.